So last time we talked about modular arithmetic. You can do these mathematical operations on the numbers from 0 to n minus 1. But what are the actual algorithms you can use to do those computations? We didn't actually describe that, just what the properties of those operations are. So let's consider the actual algorithms that we'll need to do these operations. Okay, so some of the classic things we need to answer are, how do we add x and y mod n? How do we multiply x and y mod n? And how do we raise x to the y mod n? All of these things will be important. For now, we're going to assume that x, y, and n are little n-bit integers. So you can assume that x, y, and n are all less than or equal to 2 to the little n. So here's a very basic question. Notice that to do modular arithmetic, I have to get the remainder upon division by n, right? I want to take x mod n. I need to get the remainder of x upon division by n. So how do I do division? I haven't talked about that yet. We talked about multiplication, right? We had two n-bit integers. The first algorithm we had for multiplication required O of n squared computation. We had a slightly faster algorithm that was n to the log base 2 of 3, if you recall, using a slightly smarter formula from Gauss. But what about division? How do we divide two n-bit integers? Let's try that now. Okay, so here's an algorithm to divide two n-bit integers x and y. I don't want to explain this algorithm in full detail, but I'll just give you the sense of what's going on here. Remember that you can always write x as some multiple of y, let's say q times y, plus a remainder of r, right? And that you want that r to be between 0 and y minus 1. The trick here basically is to do essentially a divide and conquer strategy where you take x and you divide it by 2. You might have to floor it because x may be an odd number. And then you recursively call the divide function on what is roughly half of x. And then, of course, you got an answer, q times r. You fix it with this 2q and 2r because you did this with a half of x rather than the full x. And then you may have to do some corrections down here, right? These are just correction parts to fix the fact that x might have been odd. You also halved x to do this, and also you might have gotten a remainder that was not between 0 and y minus 1. I'm going to let you think about the correctness of this algorithm. It's actually an exercise in the book. But I'm just giving you a sense of what this algorithm looks like. What we really need to do is figure out how fast this algorithm is, what's the running time in terms of little n, since these are both n-bit integers. Okay, so to look at the running time, let's just look at some of these operations here. You'll notice that if we just look at, let's say, these operations right here, right? I have to check if x is equal to 0. That kind of takes O of n time. I'm going to have to look at all of the bits of x and make sure that they're all 0. Returning q and r as 0, that maybe takes O of 1 time, and maybe doing the return call maybe takes O of 1 time. But still, overall, this might take O of n time. Remember, n is the number of bits of x and y. Let's skip the divide step. We'll get back to that in a second. Here, doubling q and r, multiplying them by 2. That takes, I guess you could say maybe that takes O of 1 time, right? This call right here. Checking if x is odd, that's probably an O of 1 operation. Adding 1 to something, that could be an O of n operation. I guess it depends on how you do it. It could be that you have to, keep carrying the 1 over as you, add bits to this number r. Checking if r is greater than y, that's going to be an O of n operation. Setting q and r to be q plus 1 and r minus y, that's going to be an O of n operation. And then returning them, let's say that's an O of 1 operation, right? Let's go here. So overall, though, we have all of these O of n operations. Everything is on the order of n. The only question is, what is this divide call? It turns out that this divide call, you might want to say that this reduces the size of n to n over 2, right? You might want to say something like t of n equals t of n over 2 plus O of n. And it turns out that's not true. It's not true. Why isn't that true? Well, it turns out that n is a number of bits. If you divide x by 2, you actually only remove one of the bits. So I have to fix this and actually say this is simply t of n minus 1. T of n minus 1, unfortunately. Okay, so I can't really use the master theorem here because I'm not dividing the input to t by a factor of b. That's what I need to use the master theorem. But this is a pretty easy recurrence relation to figure out. Just notice that I can write that t of n is less than or equal to c times n, right? That's the O of n term, plus t of n minus 1. And I can keep going through and reducing t of n minus 1. That's going to be less than or equal to cn plus c times n minus 1 plus t of n minus 2, right? And I can just continue to unroll what this thing is. And I'm going to have this is less than or equal to dot, 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 c times n plus n minus 1 plus n minus 2 plus dot, 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 plus 1, right, plus t of 1. And what's going to be t of 1 there? T of 1, I can just assume that this guy right here is some O of 1. Now, that's just going to be the return call or whatever. Okay, so in total, what is this? If you know what the sum of the first n numbers is, this is actually going to be, roughly speaking, well, let's just say this actually equals c times n plus 1 over 2. If you've ever looked up the nth triangular number, it's the sum of the first n numbers, you end up getting something which is on the order of n squared. So this whole thing is on the order of n squared. So now what we have is an algorithm for division that takes on the order of n squared. It turns out we can do better than this, but let's just stick with an O of n squared algorithm for now. That's not too bad. It's a small polynomial in n. Okay, so let's get back to trying to answer the question of how to do some of these basic operations. Let's say we have x, y, and capital N are all little n-bit integers. How do I simply add x and y modulo n? This is actually pretty straightforward, right? First, you just add x plus y as ints, right, as integers. And then you might have, it might be the case that x plus y is suddenly larger than capital N, right? So if x plus y is greater than or equal to n, then subtract capital N, right, from the sum. And that's going to be the output. You can just return that. That should be between 0 and n minus 1. Okay, what about multiplying x and y? Again, you can just multiply as integers. And again, you can simply then compute remainder of x times y divided by n, right? Just get the remainder upon division by n, and that's what you want, right? That's how you get x times y modulo n. We've already learned that that's going to be an O of n squared operation, so the whole thing is going to be running time t of n is equal to O of n squared, and for this guy up here, of course, t of n is going to equal just O of n, right? You just have to do a sum, which is an O of little n operation, and maybe subtract off this capital N. Again, that's an O of little n operation. All right, so addition and multiplication, those are pretty straightforward. What about exponentiation and computing inverses? Those are actually going to be a little trickier to get the right algorithms, and we'll have to do some more care. Okay, let's look at exponentiation, and let's just focus on ways to do exponentiation. I'm just going to quickly show you a bad idea for doing exponentiation. One way you could try to exponentiate x to the y mod n is to first just say, okay, first I get x mod n, x to the 1, that's easy. I just say that's just x mod n, right? And then from there I can compute x squared mod n, right, by just multiplying by x, right? That's like an O of n squared operation. And from there, of course, I can get x cubed mod n, and so forth, dot, 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 all the way down to x to the y mod n. Okay, this is a bad algorithm. Let's think about why this is a bad algorithm. How many times did I have to do a multiplication? A multiplication, right, every round of this took O of n squared. Right, every round, because I had to do multiplication, took O of n squared. So every one of these rounds took O of n squared. How many rounds were there? Well, there were y many rounds. I had to do this y number of times, or maybe y minus 1 number of times. Operations, but how big is y? Well, y has a little n bits, so y could be as big as 2 to the n. So the number of times that I had to do this is O of y times, which is equal to O of 2 to the little n, right? So total time is O of n squared times 2 to the n. right? I don't want an exponential and little n algorithm. I want something that's polynomial and n. So we have to try to find a better algorithm than this. Okay, so now we're going to do a faster method for exponentiating x to the y mod n. Okay, so first things first, we compute x mod n and then x squared mod n. Remember, we can get x squared mod n by simply multiplying x times itself and then taking that mod n. To get x to the fourth mod n, we simply square x squared mod n and then take the remainder upon division by n. And then to get x to the eighth mod n, we simply square x to the fourth mod n, and again we take the remainder upon division by n. Each of these operations is going to be an O of n squared operation, and we do this all the way up to x to the 2 to the n. So we have to do this n times. So in total, this is going to be an O of n cubed operation, this step. Okay, now that we've computed x raised to all of these powers of 2, let's think about what y is. Just assume that like y is written in binary. Let's just say it's 1, 1, 0, 0, 1, right? What that means is that y equals 2 to the 4 plus 2 to the 3 plus 0 times 2 to the 2 plus 0 times 2 to the 1 plus 2 to the 0, right? That's what it means to write it in binary. That's how we can represent it. Now notice that x to the y is equal to x to the 2 to the 4 times x to the 2 to the 3 times x to the 2 to the 0. You'll notice that each of these terms right here, right, these were all computed above. We already did these things above in the previous step. We've already gotten all of these terms. So all that's left to do is to multiply all of these things together. We're going to have fewer than n of these terms, right? And multiplying them together takes only multiplying any pair of them together takes on the order of only n squared. We can then take that modulo capital N. Okay, so let's look at the running time, right? We had to do possibly n multiplications modulo capital N, and each of those multiplications takes on the order of n squared, so the total is going to be on the order of n cubed, right? We had less than or equal to n mults of n-bit ints, right? So the running time is going to be equal to on the order of n cubed. Cool. So what's the total running time here? We had an O of n cubed algorithm to complete the first step, all these x's raised to powers of 2, and O of n cubed to perform the second step, which is just multiplying some of these terms together. The total is on the order of n cubed. This is an O of n cubed algorithm to compute x to the y mod capital N. Just to simplify the algorithm I just taught you, there is actually like a divide and conquer style version of what we just did. And I'm just going to show it to you right now. I won't go through all the details, but you can check this on your own if you like. What the algorithm does is it takes in these n-bit integers, x, y, and capital N, and it produces this mod exp function. What mod exp does is it recursively calls mod exp on the same inputs, but it tries to have y, right? It takes the floor of y over 2. And depending on whether y was even or odd, it may have to, when it uses the output of this recursive call, it may have to, well, it's going to square z, which is the thing it got from z out of this recursive call. It squares it if y is even, right? Because once you compute the exponentiation mod n, you have to get z squared because we reduced y by a factor of 2. And if y was odd, which is this case, we actually have to multiply by x here, right? We have to get this this x in here because we lopped off a 1 by rounding down from y over 2. So you can think about this and check to see why this is a correct algorithm, but it's worth doing on your own time. But I just want to focus on one thing, which is the running time of this algorithm. if we write t of n here, right, t of n is going to equal n is the size of these integers. Maybe n is the size of y. Y is the thing that's going to be shrinking. You'll notice that each of these things requires a multiplication of two n-bit integers, right? Z times z. Z is going to be an n-bit integer. This requires 3 multiplications, let's say. But again, this is still going to be on the order of n squared. We can just use our standard multiplication algorithm. And everything else is basically going to be like an O of 1 or maybe O of n operation, except for this recursive call. And again, this recursive call, you might be tempted to think that it's t of n over 2, but actually it's t of n minus 1. So in total, what we're going to get is t of n equal to t of n minus 1 plus on the order of n squared. And if you work this out, you're going to find that I'm going to essentially be adding up a constant times n squared plus a constant times n minus 1 squared plus a constant times n minus 2 squared. And if you just work this out, you'll find that this thing is going to equal to on the order of n cubed, right? But we already knew that from the more direct example that I gave you in the previous slide. So the one thing I haven't taught you yet is how to compute multiplicative inverses mod n. That actually is a little bit trickier, and we're going to save that for the next lecture. So stay tuned.